What's up? I'm Vin, and today I'm going through an AP Calculus ABBC Unit 1 practice test. I'll leave a link to a copy of this test in the description below, so let's get started. So first up here, we have a graph of f of x, and we're going to use this to answer questions 1 through 3. So for the first question, we want the limit as x approaches -1 of f of x, and here's our graph of f of x. So what we're going to do is we're going to approach from the left side, and notice here that we're getting really close to x equals -1, and our y value is getting really close to 2. But we also have to verify that the right side limit is the same. So notice when we approach from the right side that we're approaching a y value of 2. So for this one here, our answer choice here is going to be B. Just know that this one here is a very dangerous bear trap. All right, we have to be very careful. A lot of students, when they mess these questions up, simply identify the function value, but this tells us that f of -1 is equal to 3. So this is a very distracting answer choice, but choice B is our answer. So next up, now we want to find the limit as x approaches 1. So notice if we approach from, let's say, the left side, so we're getting close to x equals 1 on the left side, the y value is heading down to 0. So I'm just going to write that over here. The limit as x approaches 1 on the left side of f of x is equal to 0. But then watch what happens when we find the limit as x approaches 1 on the right side of the function. So we use the graph again, and now here's 1, we go in this neighborhood, and we follow this part of the graph, and when we get close to x equals 1 on the right side, notice we're heading to a y value of 1. And since our left side and right side limits are not the same, that tells us that the limit does not exist. Now, for the previous question, notice what we had here, this was a removable discontinuity. So this is just some background theory on Unit 1. So this is a removable discontinuity, whereas what we have here, this is actually a jump discontinuity. So we could call this one here a jump discontinuity. And then at x equals 2, notice we have a vertical asymptote. So this would be an infinite discontinuity. So this would be if we had to classify what type of discontinuity we have. So now for question 3, we want the limit as x approaches 2. And now we're on the left side. So here's 2 over here. So at x equals 2, notice we have a vertical asymptote. But if we're on the left side, notice as we get closer to x equals 2 on the left, our y value is going all the way up to positive infinity. So choice C would be our solution here. Now, if we wanted to find the limit as x approaches 2 on the right side of f of x, let's say there was another question, we get near x equals 2 and we approach on the right side, and in this case we would be heading to a y value of 1. So this is a distracting answer choice, but choice C is our answer. So question 4, we want the limit as x goes to infinity, and we have this rational expression here. So for questions like this, what you want to do is you want to identify the leading term on top and the leading term on bottom. Now, a little trap that was set here for us is that when we have the leading term on top, notice that it was the middle term, not the first term. So sometimes students will just look for what is the first term here, and they say, okay, that's a coefficient of 1 over 2. So choice B is a very distracting answer choice. But what this allows us to do when we have a limit as x approaches infinity of a rational function is we could just rewrite the limit in terms of just the leading terms like this. And notice that we have matching powers of x, so they just cross off. And then -4 divided by 2 is -2. So choice C would be our solution. So question 5, we have the limit as x goes to infinity, and we have these exponential functions on top. Now, one thing that's going to help us here as we think our way through this limit, because remember, we're going to do this with no calculator, is let's think of the graph of e to the x. This is an exponential function that goes up like this. And then if I look at the graph of e to the minus x, this is going to be an exponential function that's decaying. So it's going to be starting up and then it's going to drop down like this at an exponential rate. So then how does this help us? Well, if we go piece by piece, the limit as x goes to minus infinity, because in this question we're going to minus infinity, so it helps to just think about that limit. The limit as x goes to minus infinity of e to the x, if we go all the way left, our y value is going to head to 0. And then if I take the limit as x approaches minus infinity of e to the minus x, this would actually send us all the way up to infinity like this. And a little thought experiment you could go through is just think if you were to plug in negative infinity, let's say to the second limit, you'd have e to the minus minus infinity, which would give you e to the infinity, which would send you to infinity. So this is just something we want to be mindful of. Now, if you can do this, you could just thought experiment yourself into knowing that these two pieces are the leading terms, because when we go to negative infinity, e to the minus x, once again, is going to go to infinity. So in a way, these are the two leading terms. But if that's too confusing to think about, what you could do is you could factor out an e to the minus x on top and bottom. So if I take out an e to the minus x on top, I'm going to be left with 3e to the 4x, because you could imagine here when we multiply e to the minus x times e to the 4x, negative x plus 4x would give us 3x, sending us right back. But then I'll have a minus 1 here after I factor out e to the minus x. And now I'll do the same thing on bottom. Take out an e to the minus x, and we're going to have e to the 4x, and then we'll have minus 2 like this. So notice over here, these terms are going to cancel out. And now this is equal to, if we evaluate the limit, remember what we said, as x goes to minus infinity, the e to the positive x terms are going to shrink to 0. So now what we have is we have 0 minus the constant 1 divided by e to the 4x as x goes to minus infinity is also heading to 0. And then we just tack on our minus 2. And if we do negative 1 divided by negative 2, that's going to give us positive half, which is going to match up with choice B. So question 6, we have this limit here. And the first thing we could try is just plugging in pi over 2. But if we do that, we're going to have cosine pi over 2 is 0, and 0 squared is 0. And then on bottom, sine pi over 2 is 1. 1 minus 1 is 0. So this is one of our indeterminate forms. Now, be careful here. Some students get to this step and they're like, oh, great, 0 over 0 does not exist. But this is not necessarily the answer. It could still be the answer, but we have more exploring to do. And the secret to this question here is we have to know sine squared plus cosine squared is equal to 1. So if I want, I can make a substitution for cosine squared, that cosine squared x is equal to 1 minus sine squared. And notice what I have here. If I rename this, so I'll go ahead and do this first. The limit as x approaches pi over 2 of 1 minus sine squared x over 1 minus sine x. Now we have a difference of 2 squares on top, so we could factor. And watch what happens. When we factor, we have 1 plus sine x times 1 minus sine x. And then on bottom here, we have 1 minus sine x. And then 1 minus sine x, 1 minus sine x cancel. So now when we plug in, we're going to have 1 plus sine, and now we plug in pi over 2. Sine of pi over 2 is 1, and 1 plus 1 is equal to 2. So our answer choice here is going to be choice B. So question 7, we have the limit as x approaches infinity of this expression here. And the first thing that should jump out at people is that if you were to try to plug in infinity, you're going to have the square root of infinity, which is infinity, minus x is approaching infinity. And infinity minus infinity is one of our indeterminate forms. So this is something that we have to be careful of, because students might just look at that and say, oh, infinity minus infinity is 0. But choice B is a very dangerous bear trap we have to be careful of. So moving on here, how are we going to handle this? Well, we could just write this expression as something over 1, and we're going to multiply the top and bottom by the conjugate of the top. So we have the square root of x squared plus 8x, and now we're just going to tack on a plus x like this. And then we're going to multiply the bottom by the same thing, x squared plus 8x under the radical, and we tack on our plus x. Now on top, we could use the distributive property twice, or anytime you multiply something like a plus b times its conjugate a minus b, it's just the first term squared minus the second term squared. This is recognizable as a difference of 2 squares, but that's basically what we're applying here. So we have the limit as x approaches infinity, and if you do radical x squared plus 8x times itself, you're just going to get x squared plus 8x minus, if you do x times x, you're going to get x squared. And now on bottom, we just have the conjugate expression here. We have square root of x squared plus 8x, and then we just tack on our plus x. Now right away, I see that the x squared minus x squared is going to cancel, but then that brings us to this step. So we get over here, and this is the limit as x approaches infinity, and I'm going to leave some space here. We're going to have an 8x on top, and on bottom, we're going to have the square root of x squared plus 8x, and then plus x like this. So now looking at this, the challenge becomes like, wait, how did this simplify things? But what we could do is, since x is approaching positive infinity, one thing I want to be mindful of is that I could say the square root of x squared is equal to just x, because x is approaching positive infinity. If x was approaching negative infinity, then technically I would have to say the square root of x squared is equal to minus x. And the reason why I'm explaining all this is because what we want to do now is divide everything by x. However, this expression here, I'm not dividing by x. I'm going to divide by the square root of x squared, which is equal to x if x is approaching positive infinity. So now we start to simplify this. This is the limit as x approaches infinity of, on top we're left with just 8, and on bottom, if we divide the two common radicals like this, I'm just going to divide each term by x squared. Inside the radical, I'm going to have x squared over x squared is 1 plus, and if I do 8x over x squared, that's just going to give me 8 over x. And then I just tack on x divided by x, which is 1. So now if you think about this carefully, the limit as x approaches infinity is really just affecting this term here. And if I have 8 divided by infinity, that's going to go to 0. So I'm going to have 8 over, I'm going to have the square root of 1 plus 0. And then outside the square root, I have another plus 1. So this is going to work out to 8 divided by 2, which is equal to 4. And this is going to match choice C. So question 8, we have the limit as x approaches c of f of x equals L. Which of the following statements must be true? So for this one, I would draw it out. What does it look like if the limit as x approaches c of our function f of x equals L? And what I would do here is just aim for this point over here. So I have a graph here and it's heading in the direction of L like this. Now I have the option here of coloring this in or leaving it open, but we want to know which of the following statements must be true. So I want to try to put as many restrictions on this as possible. So choice A says the limit as x approaches c from the right side. So that's over here, like as x is approaching c from the right side, our y value is heading to L. This has to be equal to the limit as x approaches c on the left side. So this is us approaching c from the left side. So this one is definitely a statement that must be true. But of course, I would go through the other answer choices to see why they don't have to be true. So what we have here is the function value at c equals L. Well, we don't actually have to have a function value at c. We just need to be heading towards L. And I could have the function value way up here like this. And notice this is a situation where the function value doesn't equal the actual limit. So this choice is out. F of x is continuous at x equals c. Well, just know the third grade definition of continuity is that I could draw my graph without lifting my pen off the page. But this one here, I would have to lift my pen off the page to draw that point. And you can see there's a hole in the graph. We have a removable discontinuity. So choice C is out. I don't have to be continuous at C. And then what we have here is the limit as x approaches c from the left side of f of x is not equal to L. Well, this one here is just simply not true at all, because if the limit as x approaches c of f of x equals L, that implies choice A, that the left and the right side limits have to be equal. So A is definitely our answer. So question 9, we're assuming that k is constant. For what value of k is this function going to be continuous at x equals 3? Well, just know if this was the free response section here, so if this was a free response question, what we need to show is that the limit as x approaches 3 of f of x is equal to f of 3. So what I'm looking at here is if I want to find the limit as x approaches 3 of our function, I'm going to be looking at the piece where x is not equal to 3, because this is going to allow us to approach from the left and right side. So I'm taking the limit as x approaches 3 of the x squared minus 9 over x minus 3 piece. And just notice the top factors to x plus 3 times x minus 3. And we're dividing by x minus 3 like this. The x minus 3's cancel out, and when we plug in 3, now our limit simplifies to 3 plus 3, which is equal to 6. So what we need to happen here, the limit as x approaches 3 of the function equals 6, we need f of 3 to also be equal to 6. But notice what they told us in the piecewise function. This row here of the piecewise function tells us that f of 3 is equal to k. So that would tell us if f of 3 is equal to 6 and f of 3 is equal to k, k would have to be equal to 6. Choice A is our answer. So question 10 is a pure definition question. Let's say you forget what a horizontal asymptote is, and we want the line y equals a to be a horizontal asymptote. Well, then all you have to do is just draw this out. So I have the line y equals a. So this will represent y equals a. And they're pointing out here that the function f of x is even, which just means that it has symmetry over the y-axis. So for this to be a horizontal asymptote, we would need something that looks something like this, let's say, where the graph is getting closer and closer to the horizontal line y equals a as x goes to infinity or negative infinity here. But now let's scan through the answer choices. The limit as x approaches infinity of our function equals a automatically sounds good. So this is looking like our answer. But now choice B says the limit as x approaches infinity of f of x equals 0. Well, this would be true, or this would have to be true if this question changed to y equals 0 is a horizontal asymptote. But it was just y equals a is a horizontal asymptote. So a does not necessarily have to be equal to 0. We want to know which one must be true. So B is out. The limit as x approaches a from the right side of f of x approaches infinity. Well, this would be true if x equals a was a vertical asymptote. So you could imagine here that if I had a vertical asymptote like this, then the limit as x approaches a on the right side going up to infinity would tell us we have a vertical asymptote, and the limit as x approaches a from the left is also another way of saying we have a vertical asymptote. So this would be confusing vertical and horizontal asymptotes. Choice A is our answer. So question 11, we have f of x and g of x are continuous functions, and we have select values in the table. We're told h of x is this composition function here. Which of the following statements is true? So for this one, if I want to verify A, I have h of 1. I'm just going to plug into the function here. We're going to have f of g of 1 and then plus 5. So we go on a mini scavenger hunt. We go for x equals 1, and then we go over to column G. And this tells us that g of 1 is equal to 4. So this simplifies to f of 4 and then plus 5. So now I'm going to go searching for f of 4. So x equals 4, and the values for f of x here tell us that at x equals 4, f of x is equal to 21. So we have 21 plus 5, which is equal to 26. So choice A verifies, but now we have to keep going to see if choice B verifies. So far A is good, but now if we go further, what we have is there must be a value C where C is between 1 and 4 such that h of C is equal to 14. So this is shouting out the intermediate value theorem. So we already found h of 1, which is convenient. We have to check this other endpoint here. So h of 4. So if we plug in, we have f of g of 4, and then we tack on our plus 5, and now we go searching. G of 4 is equal to 1. So I have f of 1 plus 5, and now f of 1, I go over here, is equal to 8, and then that gives me 8 plus 5, which is equal to 13. So if I get a little graph of h, so here's h of x, and we look at this graph here at x equals 1, we're all the way up here at 26. And then h of 4, we're all the way down here at 13. So this is out here at 4. Now, we were told in the beginning that f and g are continuous. So what that tells us, if f and g are continuous, we have a composition function of two continuous functions plus a constant. This implies here that h of x is also continuous. And now one thing to be mindful of here is that this target value of 14 is somewhere over here. And if you think about it, because h of x is continuous, that means when I draw from this point to this point, I have to draw it in one motion without lifting my pen off the page. So no matter how I draw h of x, no matter what this looks like, this is going to have to pass through the line y equals 14. So what this tells us is that, yes, this is a must be true statement here. There must be a point C, let's say over here, where the function h at that point, x equals c, is going to be equal to 14. So this is true by, once again, the intermediate value theorem, that you have to pass through all the values between your two function values if you have a continuous function. So this one is definitely true, which tells us choice D is automatically our answer, but let's verify why choice C is no good. So h of 2, I would just plug into the function, and we're going to have f of g of 2, and then plus 5, and now we go searching. G of 2 is equal to 2. So that's going to give us f of 2 plus 5, and then f of 2 is equal to 10, and we have 10 plus 5 is equal to 15, which is clearly not equal to 20. So that's why choice C is out. D is definitely our answer. So question 12, we're just going to multiply by the conjugate of the top. So we're going to go here and say the square root of 2x minus 5 plus 1, and then we're going to multiply the bottom by the same thing. We have the conjugate of the top like this. So now when we rewrite our limit, we have the limit as x approaches 3. And on top, we have a difference of 2 squares. That concept again, because we're multiplying a binomial by its conjugate. So this is going to be the first thing squared minus the second thing squared. So if I do radical 2x minus 5 times itself, I'm just going to get 2x minus 5. And now I'm going to have minus 1 times 1 is 1 like this. And then on bottom, I'm going to leave this in factored form. So I have x minus 3 times I have the square root of 2x minus 5. And I'm going to extend that radical, and then we tack on our plus 1. So now notice what happens here, that we have negative 5 minus 1, which works out to negative 6. And then just to save time here, I'm just going to factor that all in one step. So if I have 2x minus 6, that's going to factor to 2 times x minus 3. So I had mentioned this before, but once again, the reason why we don't actually multiply those two is because the x minus 3 is going to cancel. So we're going to have the square root of 2x minus 5 plus 1, but these x minus 3's wipe out, and now we could plug in. We have 2 over, and if I plug in x equals 3, now I have the square root of 6 minus 5 is 1 plus 1, and that's going to give me 2 divided by 2, which is equal to 1, Choice A is our answer. So question 13, we want the limit as x approaches 1 of f of x times g of x. So if we look at the graph of f of x first, notice as x approaches 1 on the left side, so we're just going to find the left side limit first, that we're heading to a y value of 2. And as we approach on the right side here, we're also heading to a y value of 2. So this is going to be equal to 2 times, and notice what we have here. We said the graph of f of x is here, and we have the continuous function g of x. So since g of x is continuous, this tells us that the limit as x approaches 1 of g of x is simply equal to g of 1. So this is one really nice thing about continuous functions, is that once you know that a function is continuous, you could find the limit of that function just by plugging in. So we're going to have 2 times g of 1 here, and now we just use the table. That's going to give us 2 times g of 1 is equal to 5. So you have 2 times 5, and that's going to be equal to 10. So choice A is our answer. So question 14, we have this limit here, and this could be a little bit of a tricky limit to evaluate, but there's a nice little trick for this, that what you could do is you could think of the number line, and I'm looking at x equals 4. And if I'm approaching 4 on the left side, that's what that minus means. I'm getting close this way. I think of an x value like, let's say 3.9. That's really close to 4, but it's on the left side. And if you plug in x equals 3.9 to this limit, notice you're going to get the absolute value of 3.9 minus 4 divided by, we would have 3.9 minus 4 like this. And what we're going to have inside here is we're going to have the absolute value of negative 0.1 divided by negative 0.1. And then the absolute value is going to take care of that negative and just flip this to 0.1. But on bottom, we're going to be left with negative 0.1. And when we divide these two quantities here, we have a positive over a negative. This is going to work out to negative 1. So that tells us our answer is choice B. But if you want a more technical solution to this, like you don't want to do this by using a trick, what you want to think of is the piecewise definition of absolute value is that it's equal to x if x is greater than or equal to 0, and it's equal to minus x if x is less than 0. So what I think of for this is that the absolute value of x minus 4, if I use that piecewise definition, is going to be equal to x minus 4 if x is greater than or equal to 4, because the significance of this value here is the transition at the vertex. Like think of absolute value x, it looks like this. So at the vertex 0 is where we make our transition, but x minus 4 in the absolute value is the same graph just shifted over 4 units to the right like this. So this would be our graph that we have here, the absolute value of x minus 4, which we could just color code like this. So then if I want the second line here, this is going to be minus x minus 4 like this when x is less than 4. So then how does that help us here? Well, when we want to find the limit as x approaches 4 on the left of absolute value x minus 4 over x minus 4, we apply the piecewise definition and think about it. When we're on the left side of 4, we're less than 4. And then we could get rid of the absolute value if we rewrite that as minus x minus 4 like this over x minus 4. And then notice the x minus 4's just cancel out, and we're just left with negative 1 here. So that's another reason why this is choice B. But once again, the AP test, time is money. So just plugging in something like x equals 3.9, you'll be done in seconds, but this is a more technical solution. So question 15, we're going to evaluate this limit, and let's go ahead and use the squeeze theorem. So we have sine of 1 over x. This expression is always between negative 1 and 1. And what I want to do here is I'm going to multiply everything in place by x squared to essentially build this expression inside of our limit. So we would have negative x squared is less than or equal to x squared sine 1 over x, and that's going to be less than or equal to x squared. And just note that x squared itself is always greater than or equal to 0, so that's why the inequalities, we don't have to worry about them flipping or anything. So just kind of visualize this for a second. Negative x squared is all the way to the left here, and it looks like this. And then positive x squared is all the way to the right and looks like this. So our function sine of 1 over x times the x squared in front is always between these two functions. So it's a perfect candidate here for the squeeze theorem because we're approaching x equals 0 like this. So our function is going to be kind of like zigzagging on its way to 0 like this. You don't actually have to be able to graph this, but it just helps to be able to visualize this a little bit so you can see what's going on. So now if we think about it, the limit as x approaches 0 of minus x squared is equal to the limit as x approaches 0 of positive x squared. They're both equal to 0. So by the squeeze theorem, by the squeeze theorem implies that the limit of the middle function x squared times sine 1 over x is going to get squeezed to 0. And this is something that we could visualize right here on the graph, that as we approach 0, all three of these functions are going to 0. That middle function is getting squeezed to 0. That's why they call it the squeeze theorem. This is going to be choice C. Okay, so we're moving on now to the part 2 free response. Calculator use is now permitted. And the first thing we're going to do here, we have f of x, and we're going to fill out this table. So we're just going to go over to the y equals here. And we're going to write x to the power. And to write a nice fraction, we press alpha y equals enter. And we've got 1 over, we have 1 minus x on bottom. And now when we go to the table, the problem is that we need to get these decimal values, but we only get whole numbers. So if we press second window here, we could switch the independent variable from auto to ask. And what this does is it allows us to create a custom table. So now if I type in 0.9 for x, I'm going to get the corresponding y value. So now I'll just type in all these values. So now I'll just go ahead and transfer these values to the table. So now for part B, we're going to use the table to estimate the limit as x approaches 1 of f of x. And let's look at this table here. We're going to approach 1 on the left side, and we're going to stop at x equals 0.999. And then when we approach from the right side, we're going to stop here at x equals 1.001, because x equals 1 would be between these values here. And then look at the y values. Our limit is going to be somewhere between 0.3677 and 0.3681. So we need to pick a value between those two. So we could pick something like 0.368, and we'll round to 3 decimal places. So here's our solution to part B. So for part C, we're going to assume that the limit as x approaches 1 of f of x does exist, and it's approximately equal to our answer from part B. If we had to find the actual limit by hand, that limit would work out to 1 over e, but we would have to use techniques outside of unit 1. We would have to use the technique of L'Hopital's rule. But for now, we're just going to assume the limit does exist, and it's approximately equal to our answer from part B. So then what type of discontinuity do we have for f of x at x equals 1? And we have to explain. So for this one, what we want to think about is that if we were to investigate what is f of 1, so we plug x equals 1 into the function, and notice we have a 0 denominator. So f of 1 is undefined. And what we have to think about is that in part B, we have that the limit approached 0.368, and we're assuming that our limit does exist. So if our function is undefined, but we have a limit at x equals 1, that means we have a removable discontinuity. So now for the last part of this question, we're going to explain using the intermediate value theorem why there must be a value c between 2 and 5 such that the function value at c is equal to 0.6. So what you want to think about for this last part here is if you imagine the graph, or you could actually draw the graph out here, and this doesn't necessarily have to match the graph of our function, but I'm looking at, let's say, x equals 2, my y value is 0.5, and then at x equals 5, my y value is up here at we have 6687. So if we look at the target y value, we're looking at a target y value of 0.6 over here. Well, what we have here is that our function f of x on the space from 2 to 5 is continuous. Like, yes, technically in part C, we said our function has a removable discontinuity at x equals 1, but from 2 to 5, we're not going to have that issue. So our function is continuous from 2 to 5. So that means when we connect these points here, they're going to connect in a continuous motion. So there's no way to skip 0.6. And this represents the location here of our value c. So we just need to outline all of this when we actually write our argument. But this is what I visualize in my head to help me write my sentence. So for one, what I'm going to say here is that f of x is continuous on the space we need it to be. F of x is continuous on the closed interval from 2 to 5. Now, the next thing we need to do in order to be able to use the intermediate value theorem is we actually have to explain that our target value is between the two function values at our endpoints here. So what we could say is that since what we have here, since the value 0.6 is between 0.5 and this other value, so we could explain that with an inequality. 0.5 is less than 0.6, which is less than the other endpoint. We have 0.6687. So once we explain that the target y value is between our two function values, now we could apply the intermediate value theorem. We could say by the intermediate value theorem, which we could abbreviate, there exists or there must be a value, that we could abbreviate with a backwards capital E. So we could say there must be a value, and let me just clean that up a bit. So we have there must be a value C. C is going to be between 2 and 5. Notice that this is going to occur between 2 and 5, so we could just explain that here, such that we have f of C is equal to 0.6. Okay, so this would be us explaining why the function has to equal 0.6 using the intermediate value theorem. Okay, so here's question 2, and it's our last question. We have the function f of x, and it's a piecewise function. And for part A, we want to answer, is f of x continuous at x equals 2? We actually have to explain our reasoning. So for this, we want to do 3 things. First, we want to find the limit as x approaches 2 of f of x, and we're going to target the part where x is not equal to 2. So we could find this limit by factoring. We're going to have 3 times x plus 2 times x minus 2, and then on bottom, the quadratic on bottom will factor to x minus 3 times x minus 2. So now when these factors cancel, what we have left, we have 3 times, we plug in 2, and we're going to have 2 plus 2. Over on bottom, we're going to have 2 minus 3. And then this is going to work out to 3 times 4 is 12. Over 2 minus 3 is negative 1, which equals negative 12. But then the next thing we need to mention here is that the function value at 2 is equal to negative 12. So now we just summarize all of this. What we have here is that the limit as x approaches 2 of f of x is equal to f of 2. These two quantities here are equal. They're both equal to negative 12. So by the definition of continuity, we could say f of x is continuous at x equals 2. So now for part B, we have a few things to do, but first we're going to find the vertical asymptotes of f of x. So to find the vertical asymptotes, you need to do 3 things. First, you need to factor your function, and we already factored it in part A, so I'll just rewrite this. We have 3 times x plus 2 times x minus 2. Over, on bottom, we had x minus 3 times x minus 2. So we factor, we cancel, and then we set the leftover factors in the denominator equal to 0. So we're going to set x minus 3 equal to 0, which tells us that our vertical asymptote is going to be x equals 3. So this is part of our solution. Now to find the horizontal asymptotes, or single asymptote, we're going to take the limit as x approaches plus or minus infinity of our function. But one thing we could do here, we could actually look at both limits simultaneously here, because if we were to write the part here where x is not equal to 2, and let's say I distribute the 3, I would have 3x squared, and then when I do 3 times minus 4, I'd have minus 12. And we're dividing by, we have x squared minus 5x, and then we tack on our plus 6. And when you're finding limits at infinity, all you really have to focus in on are the leading terms. So if we look here, our leading terms are going to be 3x squared on top, and we have x squared on bottom. So this, we could simplify the limit to the limit as x approaches plus or minus infinity of just 3x squared over x squared. Because we have a rational function at infinity, only the leading terms are going to matter in determining the limit. So now x squared over x squared cancels, and our limit simplifies to 3, which implies that our horizontal asymptote is going to be y equals 3. And notice this is our horizontal asymptote in both directions. So this is our solution to part B. So now for the last part of this question, we're going to solve for the value of the constant b that satisfies this limit. So we switch back over to the y equals, and now we're just going to type in this function here. We have a fraction, so we're going to press alpha y equals enter, and we have 3 times in parentheses, we've got x squared minus 4 like this. And now we drop down to the denominator, we're going to have x squared, we've got minus 5x, and then we tack on our plus 6. So now the problem here though is when we press graph, we can't really see what's going on here in the neighborhood of 10. And if we want to find a precise point of intersection, we're going to type in y equals 10, because once again, our goal in this situation is to find out for which value of x, as x approaches what number, is our y value approaching 10. So what we could do to make this a bit of a clearer picture is we could bump up the y maximum to 20, so that way we could very clearly see this point of intersection. So we're looking for what value of x do we have to approach for our y value to approach 10. So for this, we're just going to press second trace number 5 to trace our intersection point. So I scroll over here to the second part of the graph, and I'm going to go a little bit before the point of intersection and press enter, go after, press enter a second time and a third time, and our b value rounded to the third decimal place to the nearest thousandths place is going to be, we're going to have 5.143. So our answer to part C, we needed to determine the value of b such that the limit as x approaches b of f of x is equal to 10. And using the graphing calculator here, we could see that our b value, when we round it, is going to be 5.143. And this is our solution to part C.